Okay, so now we're going to talk about number systems. Mostly we're interested in binary because binary is the language of computers, but we're going to talk about how we get to binary, right? And how really any number system can represent anything. We're used to base 10, what we call decimal, but they're all the same. And we're going to talk about how they're related, all right? So that is what this second half of the chapter is all about. Let's talk about the number system that we're all used to, base 10. If we have something like this, 536. Now, you look at 536, you know what it is because you've been using base 10 numbers since you were, 10 years old. So it just makes sense to you. You don't even think about it anymore. But there's a pattern there. Each one of those numbers has meaning that has to be interpreted. You've done it so many times it's automatic, but let's back up so we can understand what these symbols mean and how that relates to what we're going to learn this week. So what this really means, if you go back, let me change colors. Okay, so if you remember back to elementary school, you remember that this is the hundreds place, this is the tens place, and this is the ones place. Another way of looking at that is to say that this is 10 raised to the 0 power, this is 10 raised to the 1 power, and this is 10 squared, right? 10 times 10 is 100. You never thought about that while you were in school, but that's what that means. So literally, when you say 536, what you mean is 5 times 100 plus 3 times 10 plus 6 times 1, which is the exact same as saying remember that from math? Any number raised to the 0 power is itself, or excuse me, is 1. That's what that is. Any number raised to the 1 power is itself. So that's what 536 means. It means 5 times 100 plus 3 times 10 plus 6 times 1. You just don't think about it. So knowing that, what does it mean if I have a binary number that looks like this, right? It's a base 2 number system. Well, let's go ahead and draw our chart. Let's start at the bottom. So this is 2 to the 0 because it's a base 2 number system instead of a base 10 number system. This is 2 to the 1. This is 2 squared. 2 to the third, which is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the third power is 8. So what this literally means is since we know that anything times 0 is 0, we can cross those parts. So anywhere you have a 0, you can essentially cross that off. Anywhere, we also know that 1 times anything is itself, so we don't really need that 1 times. So what we essentially have is 8 plus 2 or 10, right? The value is 10, and it's written in binary as 1010, but it means the same thing. The key thing that I want you to understand is that for any number system, they're all the same. You're just going to have different bases, and you're going to have a different base, which means the base affects which symbols you use, and it affects which places you have. So for base 10, our places are powers of 10, 1, 10, 100, 1000. For binary, our places are powers of 2, 1, 2, 4, 8, 16, 32, 64. As you go through your computer science degree, these powers of 2 are going to become second nature to you. You should really just drill them until you have them in your head. It's going to come up a lot. All right. Okay, so that makes sense. We have our base 10 and our base 2, right? Decimal and binary. What other number systems can we use? Well, a very common one that we use a lot in computer science is octal, base 8. So with octal, I might have a number like 731. And again, we're going to draw our chart. This is the ones place. This is octal, so this is going to be the eights place. And this is going to be 8 squared, which is 64. Okay, which is again 8 to the 0th power, 8 to the 1's power, 8 squared. All right. Which means that this is 545, right? So 731 in oct, we would write that as 545 in decimal. But the key thing, I really want you to kind of get this in your brain box, all right? We can write the same value any of these ways. It doesn't matter. We need to understand the difference between the value and the way we represent that value. I want you to get that in your head. Finally, let's take a look at another common numbering system that we use a lot in computers, which is hexadecimal, or base 16. So with hexadecimal, we have digits that go beyond 0 through 9, right? 0 through 9 is base 10, but how do we represent 10 in hexadecimal? We do that using A. So A is 10, B is 11, C is 12, all the way on to F, which is 15. So again, we draw our chart. So the 1s, the 16s, the 256, and the 4096 places, which is, of course, 16 raised to the 0, 16 raised to the 1, 16 squared, and 16 cubed. So because this is A, remember A is 10, so that is 10 times 4096. And I'm not going to add those up. But if you add those all up, you will get the value of A085. All right? So these are our common number systems that we're going to deal with in this course and that you run into a lot in computer science. Decimal, because that's what human beings use. Binary, because that is how the computer actually represents things. We'll talk about that in a second. Oct, which is base 8, and hex, which is base 16, because binary very easily converts to those. All right, so I want to kind of talk briefly now about symbols and some of the symbols that the book uses and some of the symbols that you should be familiar with these different numeric representations. So obviously you have for binary, we have two symbols, 0 and 1. The important thing to remember is that the first symbol of any symbol set is always nothing, right? It represents the absence of any value. And other than that, the only thing we can say about them is that each one in ranking represents more. So if we're looking at base 2, there's 0, then 1. If we're looking at base 8, octal, there's 0, 1, 2, 3, 4, 5, 6, 7. Now, another thing I want you to notice, this is base 2, and there are two symbols here, but notice it stops before 2, right? This is base 8. There are 8 symbols, 0 through 7. 7 is 1 less than 8. So that's the pattern you're going to find for all of these number bases. Always the highest digit is 1 less than the base. Decimal is 0 through 9, as we're well familiar at this point. And as we talked about with hexadecimal, base 16, then things get a little bit more complicated. We don't have enough of what we consider numeric digits. So what they decided to start doing is using the alphabet. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. But really, they could have used anything. You can use any symbol set to represent your the numbers that you want. Do people even know where ours came from? I tell you what, extra credit if you figure out where our numeric system came from. But they're just symbols that you picked. In the book, because of that complexity, they use this kind of symbolism. And that allows them to represent really high number systems. We're going to talk in a minute about a 256 base number system. So you can have 254 and 255. And remember, if it's a 256 base number system, the highest digit's going to be 255, one less than that, because we start at 0. So that's the number system that they use in the book, or excuse me, the symbolism that they use in the book. Honestly, in real computing, that doesn't even come up, because you're always using binary, hex, oct, or decimal, right? One other thing I want to point out, suppose I have the number 372. Now, is that 372 in decimal? Is that hexadecimal? Because those are all valid hexadecimal symbols as well. Or is that oct? Because that's a valid octal number as well. Typically, in computer science, we traditionally, if it is a base 16, we add a 0x in front of the number. And if it's not base 16, then it is decimal, right? Usually, if you have a number that ends up being like 1011, it could be decimal, but it's probably going to be binary. So we don't really, we don't prepare for that eventuality. Base 8 octal isn't used nearly as much as hexadecimal. So this is traditionally in computer science how you do it. If it's hex, hexadecimal, you put a 0x in front. If there's no 0x, it means binary, or decimal. However, that's kind of imprecise. So when we're doing math, we tend to use the subscript method. So I would subscript this as 10 to make sure you know it's base 10, or 16, so it's base 16, or 8. So I would write that as a subscript for each number. I don't particularly care when you're doing your work, whichever way you want to do it when you turn in stuff to me, but know that the book and most mathematical textbooks will use that subscript to indicate the base of the number system. And honestly, it is a better way to do it. However, you can't do that on a computer, right? Certainly not on a traditional text terminal. So putting 0x in front made a lot of sense to original computer scientists, okay? All right, so that's all I want to say to kind of introduce the concept of number systems. We're going to get into computer arithmetic and how computers use these symbols to do math and that type of thing as we go through the rest of this chapter. If you have any questions, ask them in the forum below.